We've just shown that if we had a sorted list, we can search it much more efficiently than just linear search. And that's great. But wait a minute. How do I get a sorted list? What if my list's not sorted? What's the cost of sorting? Have I just kind of played a slick game on you here? So the question we want to ask is, gee, is it better to actually sort a list and then use the binary search to find things? Or should I just stick with linear search? So let's assume that the complexity of sorting a list is just something we'll call order of sort of L. We don't know what it is here in a second, but we'll come back to it. So then what we're really asking is, if we sort and search, we want to know, is the cost of both sorting and then doing binary search, which is great, is that less than just doing straightforward linear search? In other words, is it better to sort and search, or should we just stick with the linear search? Well, if we don't know anything more, unfortunately the answer is it can't be better, because we can't possibly sort in less than linear time. Why do we know that? Well, we've got to look at least each element of the list in order to sort them. That says we've got to look at least the length of the list. So sort has to be at least linear. And if that's the case, then it sounds like it isn't better to do sorting before we do the search. But that seems disappointing. And in fact, it is because we're not completely taking into account everything that we want to do. Suppose we want to actually search a list more than once. We want to search it, let's just say k times for some value k. Then the question we want to ask is the cost of sorting plus k searches less than the cost of just k linear searches? And you can already see it's going to depend on k, and it's going to depend on sort, but one expects that if the sort can be done efficiently, then it is going to be better to sort first and then search. This is what we refer to as amortizing. We're spreading out the costs. We're spreading out the cost of sorting over multiple searches, and doing so may well make this worthwhile. So now the question is, how efficiently can we sort? Because if we can do it well, we really may be better off using binary search. And that takes us back to where we started, which is to say, then we can reduce a lot of search problems just to a known solution, which is binary search. Okay, so let's look at sort. And we're going to look at two examples. The first example is shown here with a piece of code. It's called selection sort. And the idea behind it is pretty simple. Given a list, we're going to find the smallest element in the list and swap it with the first element. And then we're going to take the remainder of the list, find the smallest element of that, and swap it with the second element. And just keep doing that until we've done the overall search. So you can see that here. I'm running a loop over the range of the list. I start off saying that the location of the smallest thing is at I. I've got the minimum index is I, and the minimum value is the value at that point. I'm going to start j at 1 more than I, and then I'm going to run through a loop where I walk through the right-hand side of the list, and I find basically the smallest element. If the value right here at j is smaller than the smallest thing I've seen so far, which includes the thing I'm about to swap with initially, then I just change those things. So this basically says, find the smallest value in the right of I, or to the right of I should really say. Okay? And when I've done that, okay, I'm going to run through that entire loop. Then down here, I just do a switch. And I have to be careful. I'm going to temporarily hold on to the value at the ith location of the list, using temp, right there, so that I can take the thing at the minimum location, put it into I, and then take that temporary thing and put it there. So this is a standard way of doing a switch. I temporarily hold on to something, so I move into that location, and then take the temporary thing and put it into that spot. So you can see this is doing, again, what's called selection sort. I find the smallest thing, I move it to the front, I find the next smallest thing, I move it to the next location, and I keep doing it. Okay, let's look at this. First of all, let's analyze this selection sort. And one of the things, again, I'd like to know is to be able to determine, does it really do the right thing? And I can do that by identifying what we'll call a loop invariant, something we've seen before. And the loop invariant basically says, here's a property that holds true at each stage through the loop. And if I can do that, then I can reason about, does it satisfy the base case? And does it satisfy that induction step of if it's true for a smaller version of the problem, is it true for the next version of the problem? And if I do that, then I can show that I'm done. The loop invariant here is pretty straightforward. it says given a prefix of the list, the first half of the list, and a suffix of the list, everything after the ith location, then the loop invariant is going to be that every time I go through this loop, I'm going to claim that the prefix is sorted, and that there's no element in the prefix that's larger than the smallest element in the suffix, that everything in the prefix is smaller than everything in the suffix. Okay, that's my loop invariant. Let's see if that holds true. Well, in the base case, the prefix is just empty, so it's trivially sorted. The suffix is the whole list, and it's trivially the case that everything in the prefix is smaller than the smallest thing in the suffix. Okay, now what about the induction step? This basically says when I enter the recursive call, I'm assuming, or I know, that the prefix is sorted. So what does this say? The induction step says we're going to find the smallest element of the suffix and move it to the end of the prefix. If the prefix was sorted beforehand, putting something that's larger than everything in it at the end says the prefix is still sorted. And since I moved the smallest element, it says that there's nothing in the suffix that is smaller than anything in the prefix. So the invariant, if the invariant was true before the move, the prefix is sorted after the move, and I've guaranteed that in fact I've done the right move in. And when I exit, when I've gone all the way through all of this, what do I have? The prefix is the entire list, suffix is empty, and so I'm guaranteed that the list is sorted. Nice little induction proof that shows that I'm actually doing the right thing. Great. Now, what's the complexity? Well, what have I got? I got two loops. This inner loop down here, we already know from earlier versions how to estimate that. The complexity of that is on the order of the length of the list. Yes, the list gets smaller each time through, but basically it's the order of the length of the list. Okay? So that's the inner loop. What's the outer loop? Well, I go through the outer loop, basically order of the length of the list times. So I'm doing something of order length of L, and I'm doing that order length of L times. So the overall complexity here is quadratic. Okay? It's length of the list squared, because I got to go through the list at least once, and I got to do that at the length of the list times. And unfortunately, we know this is expensive. It's not what we would like. But it gives us a simple kind of sorting algorithm. Now the question is, all right, if I just use selection sort, would I really want to use this compared to linear search? And the answer is probably not. If it's quadratic to do the sort, and then I'm going to do order log to do the search is nice, but in general, it's going to be way too expensive to do a quadratic thing as compared to a linear thing. I need to know, can I do better?